This video will help you get started with Assignment 23 as you explore how functions can be defined by integrals. As the fundamental theorem of calculus has stated, the integral from a to b of f prime of t dt is equal to f of b minus f of a. In other words, the area between a derivative graph and the x-axis, or the t-axis in this case, on the interval from a to b is equivalent to the change in height of the function f who had f prime as its derivative. So by using this principle, what we can do, instead of finding the change in height between just a single set of points, we can go ahead and find the change in height between multiple sets of points and plot those values as a set of outputs on a new graph. So let's take the following as an example. Let's create a function y1, which is defined as the integral from 0 to some arbitrary value x of the function 2t dt. We're going to choose the numbers -3 to +3 to plug in as various values for our upper limit of integration. And I've created a GeoGebra visualization to help us calculate those rather quickly. So here I've listed out for you what each of these integral outputs will be represented by. So the first one being the integral from 0 to -3. Since we're going and traveling from x equals 0 to x equals -3, we're traveling from right to left, we need to remember that we need to be taking the opposite of our area quantities. So taking the opposite of area quantities that were positive above the x-axis, or taking opposite of negative area quantities below the x-axis. 0 to 0, well, how much area has been accumulated there? Not a whole lot of area. As a matter of fact, no area has been accumulated, so we might as well fill that in. But for x equals 1, 2, and 3, we're traveling from left to right, and therefore areas above the x-axis are considered positive and accumulated as such, and areas below the x-axis will be accumulated as negative areas. So let's use our visualization to help us out. So here's our GeoGebra visualization. So the area accumulated from 0 to 0 under the curve 2t dt is indeed a quantity of 0, which has been highlighted here in our table. So if I go from 0 to an upper limit of 1, the integral is a value of 1. Integral from 0 to 2 is 4 units of area. The integral from 0 to 3 is 9 units of area. Now there is some symmetry with this graph over the origin, so we should see some of that reflected in the data. So once again, I'm back at 0 here, so if I go 0 to -1, while the area was negative below the x-axis because we're traveling from right to left, we're taking away that negative area. So the opposite of a negative is a positive. If we go from 0 to -2, that would have been -4 units below the x-axis here. However, we're taking away that amount, so because we're moving from right to left, so the opposite of a -4 is 4. And I have a suspicion here that if I go to -3, guess what? Yep, it's a value of 9. All right, now I'm going to go ahead and plot my function y1. So here's a graph of y1. Hopefully, in thinking about the content that we learned in the first semester, hopefully this will make a little bit of sense. If my derivative function was a linear function 2t, the function that had it as its derivative should be a quadratic. In thinking about the green dotted line function here, which is the derivative graph, the derivative had a negative height value over here, which meant that the original function was decreasing on that interval. Over on this side of the y-axis, the derivative graph had a positive height value. Therefore, the original function f should have been increasing on that interval. And from another vantage point, the derivative graph, shown here once again as the dotted green line, was always increasing, which meant the slopes of the original function were always increasing, meaning y1, it was always concave up.